Okay, in this example, we're going to take a look at a ring of charge. And the ring of charge is actually a pretty simple symmetry to look at. And there are logical arguments that you can go through which greatly simplify the overall solution to the problem. My only real issue with that is that if you can't go through the problem rigorously, then when you get to the more complex problems which are similar, you don't really have a good idea on how to set up the problem, and you're quite likely going to feel an awful lot of frustration coming from that. So I never recommend that you learn how to do a shortcut on the outset of anything. When you're learning something new the first time, you need to make sure that you're going through it rigorously so that you can add that skill to your skill set. And so that's what's going to happen in this situation. We are not going to do all the logical arguments that really greatly simplify this particular example. So let's begin first by identifying what the constants and variables of the problem are. So for our constants, we have r, the radius of the ring, capital R, that's going to be a constant. The distance from the center of the ring above it is also a constant. The angle that is made by the field vector is going to be constant as well, because you're always the same distance from the edge of the ring. So theta becomes a constant. R, the distance from the edge to the point, is little r, is also constant. So the question becomes, what's variable? And the answer is nothing. Nothing is varying here. And that's also what makes this a very tempting problem to solve using less rigorous methods. But we want to go about it in a more rigorous manner. So we start by writing E is equal to the integral of k dq over r squared. Now, if we assume this is a positive ring, then the field is going to be pointing up and to the right for this chunk on the left, and this chunk over here on the right, the field is going to be pointing up and to the left. So what that means is the horizontal components cancel out, and we're only interested in the vertical components. Well, if we use this as our angle theta right here, then the vertical component will be given by the cosine function. So we can write cosine of theta here. Now, just like before, we know that dq is equal to lambda and a length, and in this case we're going to use ds. Now the reason we're using ds is because we're talking about a circle, and we use arc length to determine the length for portions of a circle. So we get E is equal to the integral of k lambda ds over r squared times cosine of theta. ds is going to be made up of capital R d theta. Now I want to be careful here to distinguish between the thetas, because we actually have two thetas here. When we integrate this, we're going to be integrating it from one point, and we're going to go around the circle. And so there will be a theta in here. So instead of calling it theta, I think it might be better to use a different variable. So let's say that this is beta. All right, so this becomes ds is equal to r d beta. Okay, so we get E is equal to the integral of k lambda r d beta cosine of theta over r squared. So E is equal to the integral of k lambda r over r squared d beta. And now to get cosine of theta, we know that cosine theta is equal to the adjacent over the hypotenuse, which is z over little r. So we get E is equal to the integral of k lambda r over r squared d beta times z over r. And now we can get E is equal to the integral of k lambda r z over r cubed d beta. All of this is constant, so we just need to figure out what are my limits of integration on beta. Well, we're going all the way around a circle, so we're going to start at 0 and we're going to take it to 2 pi. So we get E is equal to k lambda r z over r cubed times the integral from 0 to 2 pi of d beta. And the integral of d beta is just beta. So we end up with k lambda r z over little r cubed times beta evaluated from 0 to 2 pi. So this gives us E is equal to k lambda r z over r cubed times 2 pi. Now, lambda is equal to q over L, and if we want to know what q is, then q is equal to lambda times L, but L in this case is arc length, which is 2 pi capital R. So by using 2 pi r, or combining 2 pi r with lambda, we just get the value of q. So E is equal to k qz over little r cubed. And then to get this in terms of our constants, we get k qz over, now remember that r is the square root of capital R squared plus z squared. So let's just take a look at that again real quick. This r, little r, is equal to the square root of the two sides of our triangle, which is capital R squared plus z squared. So again, we're putting this back into terms of our constants, the things that we know. So this becomes r squared plus z squared to the 3 halves. And this is going to be our final answer.